Okay, so what we're going to talk about today, at least first here, is shaders. So we'll start in Unity, and I've got an empty scene. I'm going to set the stage a little bit by creating a cube and then creating a material. So um, we talked a little bit about lighting and texture mapping and all that, and we'll kind of review some of that as we go forward here. But the material is the starting point for where all of this happens, right? So we're going to create a test material. A material is in some sense a wrapper for a shader. So the primary thing we care about on a material is a shader, and then the material lets us set the properties on that. And this is true for both Unity and Unreal, and we'll look at Unreal here in a little bit. So the standard shader is, we'll kind of look at that in parts. We're going to build up a shader from the ground so we can see what parts go in here. We're not going to look at all of the pieces of the standard shader. But we'll get a sense for how that works. So what we're going to do is create a shader here to fill in for our material, and we'll see how the parameters show up here. It's very similar to creating a script, except that you're creating kind of a visual script in this case. So we're going to go in and we're going to create a shader like this, and in this case we're not going to go too interesting. We'll just use the standard surface shader here. And then we'll come back and talk about what the standard surface shader means. So first let me bring up the view of that shader. Okay, so what we're looking at here is our surface shader. Let's ignore the rest of this file at the moment. What we care about is this function, the surface function. And this is, so Unity is doing a lot of work for us. It's essentially bringing us down to this point where we output some values, one for each pixel, right? And we're actually outputting more than just the color. We're outputting, so albedo is the color, it's the reflectivity. So albedo is a term that means reflectivity of a substance, material or substance based on its reflectivity of light, right? And so there's some parts that get absorbed, some parts that get scattered. Albedo is really just the pure reflective color, and the other bits, if we're writing a shader like that, we might care about that. But just recall that albedo means color. It's a sort of fancy term for that. So that's kind of the main one that we care about. But there's these other parameters like metallicness, smoothness, which all go into the standard pipeline. And we'll kind of take a look at that. I don't define. We'll probably look at it as the specular highlight versus the metallic highlight, but it's very, very similar. So if you recall, if we go back to the whole process of texture mapping, you remember that we've defined our model as a number of triangles that are connected and an index buffer and a vertex buffer. I'm not going to go through all those slides again. I'm just going to remind you that we have this process that we transform our triangles from object space into world space, and then from world space into camera space. And then we go through the clip and all that, and we wind up with a triangle that's at the end that we want to output. And we do a bilinear interpolation over the triangle. And what we get is a lookup at each pixel. Okay? And so the surface shader that we're writing, or the surface shader, the piece that we care about is essentially the surface shader is going to be called once for each one of these points, right? So all of the work that Unity is doing for us is setting us up to say, here's the new pixel. Okay, what color do you want to put there? Okay, here's the new pixel. Okay, what color do you want to put there? And so you can look up any number of things like your position in space, your position at that pixel relative to the lights, the normal value at that pixel, the UV values of that pixel. In fact, the simple shader that we have so far is really doing just that. It's saying, what is the UV value at that pixel? Go look it up in the texture map, the main texture map, and then render that color. All right, so let's look at that. So we have this text 2D that says, what is my UV at this pixel? And I said we sort of have this magic in parameter that is coming from Unity, and then let's treat it as magic for now. In this case, it gives us a UV for the main texture, right? And so we say, go look up in the main texture what that UV is and give us that color. Now, the interesting thing that happens in shaders, and probably you'll see this all over the place, so it's good to know, is that often what you're dealing with is color, but you're dealing with color as a floating point value, color as a 0 to 1 value. So 0 is black, 1 is white, or really 1 is the full color, so you're still RGB and alpha, right? So we even see the RGB here. So in this case, by default, we're all 1, 1, 1, right? So we're getting 1, 1, 1s out of here. This is 1, 1, 1, and we're multiplying 1 by 1, and so we just get 1, 1, 1, right? So we get a pure white color coming out at this point. And then our alpha value in this case is also 1, Usually alpha means the other version, but in this case, our alpha being fully 1 means that we're fully opaque, right? We can't see through it. But what you find in shaders is that we're going to do a lot of math by multiplying colors by colors, or floating point values by colors, or floating point values by floating point. And so we don't really normally care anymore whether we've got an integer or not. It's all just floating point values everywhere. Sometimes we might allow a half, and that just means a half precision floating point value, right? So you can't represent quite as much detail in those, but you don't care because it's a simple color in those cases. Or the fixed means that it's a fixed point value, and again, still just, you know, a little less precision. It's still all floating point values in some cases. So you can just think of all these things as floating point values. It's only if you're trying to optimize that you care about that. The other version that you care about is whether or not it's a vector value, right? So we talked about, you know, multiplying, or we've sort of talked about vectors several times. So all colors are really either 3 vectors or 4 vectors if they've got an alpha value. So they're RGB. Each of those channels can be thought of as a vector itself. The UVs are a 2-vector, or 2-channel vector, or two-dimensional vector that looks across the space, right? So 2 dimensions meaning U and V, and then we're going to look it up that way. And then we can even get our position back if we really want to, if we really care about where we are in 3D space at that particular point, right? So again, after we go through the entire transformation, this pixel, we might actually care about where it is in 3D space. Usually we don't. Usually we only care about things like, you know, what its normal is, what its position, or what its direction is relative to the light, and things like that. And you know, as you can see, these slides will go peek at some of those things. So at the top of the shader, we're specifying a number of parameters. The color, the texture that we want to have associated with it. We could specify multiple textures, and usually you do. So you'll specify a bump map, you'll specify often like a surface or a specular map, or like a metalness map, metal smoothness map, that kind of thing. But you can start to define all of this stuff yourself with your own customizations as you redefine these things rather than what the standard shader does. And so we're going to break this down and look at some of these parts as to what the standard shader does, and pull some of the complexity out, hopefully. But we're going to see how it's built up, right? So all these things are parameters. We've got color, which again, you know, color just means that it's now a 4-vector, right? So we've got RGBA, and the default value is 1111, right? So our color is defined as this. So this is going to be the parameter that we'll see in Unity. We'll take a look at that in a minute. We get all ones. Same kind of thing with the texture, right? So this is the default value. If you don't specify anything on the textures, you can assume it's a white texture. I can change this to black, and then it's going to assume that my texture is black. In this case, you know, white is the sort of doesn't change anything value, because if you multiply by 1, it doesn't do it. If you multiply it by 0, then you get 0. And so black kind of takes over everything, and white just says ignore everything else, right, in terms of the math that's going to happen. And then we have a glossiness value, which is really just a single floating point value. So again, we're not really caring about specifying float anymore. We're really caring about specifying how many we're seeing, right? So we're saying, oh, it's a color, so it's a 4 value. It's a texture, so we need both a texture, a 2D texture, and we need the UV values. So really we get both of those by specifying this 2D here. And there's other kinds of textures that we can specify. There's actually 3D textures. And then here we're saying this is just a floating point value, but we're giving it a range, right? And so most often you specify a floating point value with a range, and then it's going to give you a slider. And again, we get a default value. Same with the metalness, okay? And so all the surface shader wants from us, because it's going to do a lot of work after we pass out of this. So it did a bunch of work to get us in here. It's going to do a bunch of work on the other side to get us back out of here. And then all it really wants is for us to fill in each of these values, right? The albedo, the metal, the smoothness, the alpha. There's actually a few others that we can specify, and we'll look at some of those too. But in this case, yeah, it's very simple, right? So we're looking at our texture. We're then multiplying by the color. So this is filtering the color, tinting the color, however you kind of want to think about it. And then that's our output. Then we output just directly the metal color, right? So we take the metallic value in off of the material. We pass it straight through. This part here just essentially passes it through for us. And then we get that metal back out here, and the same with the smoothness, right? So we've got this glossiness parameter or smoothness parameter. We pass it in as glossiness, and then we pass it through as glossiness. For some reason, they decided to change the name from smoothness, glossiness to smoothness, right? Odd combo of things. Okay, so let's take a look at Unity and see. So the material that we start with has the standard shader, which has a whole lot of parameters. And again, really, these are the outputs that we're going to end up doing. But we've got a custom shader, so let's look at that. We've got custom test shader that we created over here. We could change the name of custom here and it'll show up with a different subdirectory, but custom's nice because that's what we're doing. We've got our test shader, and so we see a one-to-one mapping, right, of the color to color, albedo RGB, that's actually the text that goes in here, that we're getting albedo RGB out, and it's letting us specify textures, also lets us specify the tiling and offset. I'm not going to worry about that too much. Really, that just modifies our UV, right? But if you played with tiling and shifting your textures, you can take a look at those. Let's not get into that detail. We've got our smoothness and we've got our metalness, right? So for instance, if I bring my smoothness up, then I've got kind of a plasticky surface, right? And again, all of this is really just, I've got this white color and a white texture because again, if I don't specify anything, it's going to assume it's white. And then I can differentiate between metallic and smoothness here and just see what those parameters do. All right, so I can have a very smooth metal surface, or a very rough metal surface, or a very smooth metal surface, which of course is essentially a mirror. I can have a very rough sort of plasticky surface or a very smooth plasticky surface, and we see a lot of the difference in those. And then the tint, again, so we know that, let's put our smoothness at like 0.5 and let's make a plastic surface here. So we saw that our math over here, right, is we are multiplying our texture lookup by the tint color. And so our texture lookup right now is always going to return 1, because again, we just defaulted to white, and we'll get a real texture here in a second. And then the color here is multiplied by that. So really, because we're multiplying by 1 in all channels, we're just going to get whatever the color is specified over here. So we can use that to say, well, I want a red texture, right? Or I want a blue texture, and we're going to get whatever color is in here, okay? And so that's how we get this output. And so just with these parameters we're specifying, we can specify a whole lot of stuff. Okay, so let's look at shaded textures here. So I've downloaded a couple textures. Actually, I really like this one because it's a grayscale texture. So let's look at what happens with the grayscale texture in here. I get this, I get basically a blue tint on that. So let's put it back to white. Let's see that. Actually, I'm going to remember to put this material on my cube. So if you haven't already seen this kind of thing, every object you create is either going to have the texture that you defined, or the material, or default material that comes in from your FBX import. But of course, you're going to, if you're writing shaders, you're going to need to create a material in it and change it. So you'll do that, right? So hopefully your FBX import will have all your UVs defined, just like this cube does. It will have a bunch of textures. Normally, it's going to come in and give you like the standard shader, right? The one that we started off with that we saw over here. In this case, we're talking about changing it up, so we're going to change it up here. Okay, so we've got a cement block, right? So pretty cool cement block. And now I want to look at like how the texturing works, right? So if we look at grayscale, we can think of it as just really changing the value component of the red color, right? So we're always going to be somewhere within the red, but we're going to change it either to fully red or fully black by multiplying by a grayscale value. Because the grayscale value has everything uniform, right? So it's 111 or 777, 0.7, or so on. And you can think of it as just changing all of the channels equally, right? So regardless of what other color we put in here, we'll either get all of that color or something veering towards black, right? So that's kind of the fun part of playing with a cement texture and then doing this multiplication with a tint, because we really just get exactly that tint. It's a little more complicated when you have, say, a wood texture like this one, where that really has the color, and often then the color can modify the color itself. So usually what we'll do then at that point is we'll treat this tint as some kind of gray value, right? And that'll let us specify the value component of our texture itself. And that's normally what we're going to see, right? Because normally we've already gone through and we've painted the texture. We have a color texture that we want to deal with. But you can swap these two, right? Because multiplication works either way, right? So if you have a multiplying on one on the left or multiplying by one on the right, still get the kind of the same value regardless. But the way to think about it usually is that you're probably not going to modify the tint color unless you're doing something very specific, usually you're going to just modify how dark or bright it is. Either it's fully bright when it's 1, or somewhere in between of darkness. And of course, if we multiply it by black, then we just get a black color. Now, what's cool here is that we can come in and start to play with the smoothness value. So we can say, well, this is smooth wood, and so we're getting more of a light reflection, or it's, for whatever reason, a metallic wood. Maybe we put a really glossy surface on it, or a rough but metallic-y surface on it. And so we're still able to play with those parameters to get the lighting differences. Okay, so let's take a look at what actually happens with the lighting. So this bidirectional reflectance distribution function is a complicated term which really just says we want to figure out how much reflection we're going to get from the surface. Okay? There's also a version of this that accounts for subsurface scattering and some other cool effects. Right now, we're just talking about how much light, assuming a light source, right, like the sun, comes in and reflects off a surface, our albedo, as we specified before, the reflected value, how much of that light is going to come into our eyeball. Okay? And so there's a number of ways to calculate that. The first thing that we care about is our normal, right? And so we have a normal value generally assigned from our FBX model for each vertex. So you see here the little purplish color. We usually, we could either have a flat or a smooth. Flat means that we get a copy of each vertex, and that the triangle ends up having a single value, or we share, the vertexes share their position and their normal value, and because of that, it ends up being smooth across the triangle. So we actually interpolate the normal value across the triangle. So if, say, I don't know if I have a good example of this, but if the normal is pointing off this way, and the other normal is pointing off this way, and this normal is pointing off this way, then as we move over the surface of the triangle, we will interpolate those values of the normal and get different positions for that. It's going to be smoothly interpolated by linear interpolation. So this is kind of the coarse version of roughness that we can consider as sort of a first pass. Those of you who are familiar with normal maps or bump maps, that's kind of a second level of roughness, and then we were already playing with the third really detailed version of roughness, which is a value of the smoothness that we're going to treat on the actual reflectance. So one of the most basic forms of lighting is what's known as Lambertian diffuse, which says that we kind of assume that we've got a pretty rough surface here, and there's maybe some scattering or something, and then we're going to assume that the light gets distributed uniformly in any direction given how strongly it's hitting the surface. So the only thing we care about is the power that is from the light hitting the surface. We don't care about where the eye is positioned, because once the light hits the surface, we just assume a uniform distribution of the light particles, right? So if you recall, photons light is made up of photons. There are millions and billions of photons coming in, hitting a surface from any given light source, especially the sun, at any moment. Even a single particle in space, or even a single pixel, you can almost assume that your photons are, billions of them hitting the surface. And so it's a random distribution, and so we're looking at like random little differences in the surface and where the light is hitting. But if you consider, some smoothing and then the law of large numbers, what we're really saying is we no longer care about the randomness. We're just saying we get 80%, 87% of the power, right? Because, some of the particles are reflecting this way. Exactly 13% of all of the particles of light that we see are getting reflected elsewhere. But we just take the full value of the light source and multiply by 87%, and that tells us, that's how much is getting reflected based on the 30-degree angle or whatever. Really, or it's to do with the light again, right? So if the light's coming perfectly down, then we're getting all of the light source. If it's coming in from an angle, then some of that light is going to be either captured or reflected. And of course, if it's coming in from a cosine angle, or from this flat angle over here, from a 90-degree angle, it doesn't even hit the surface at all. So what that Lambertian model captures is that the full intensity is when it's straight down a straight vertical line. We're getting all of the intensity. As we start hitting it askew, there are quantum mechanical effects that we just sort of gloss over with this Lambertian model and say, okay, it's going to do something slightly different, right? So it's going to skew off the corner, it's going to be more reflective, and all these kind of fun things that we could capture in our light model if we wanted to be really good about it. But the Lambertian model is a nice, simple one that says, let's just ignore some of those. They get scattered who knows where. And we just vary the power based on our angle, right? So the power corresponds exactly like this, right? Turns out that this is what's known as the cosine law, because this angle that the light is making here ends up following a cosine curve, right? So if it's a perfect zero, right? So if the angle is zero, we're angle to the normal. So if our normal is going up perfectly and our light angle matches that perfectly, assuming this angle is coming down, this angle here, if our light is coming perfectly down, or this WI and it's perfectly matching the N, then we get 100% of the light, and then it varies by the cosine down this way. And again, there's a lot of complexity behind that. Let's not worry about that level of complexity. There's a lot of interesting quantum mechanical effects if you want to get into that and start taking high-level physics. But for us, all we care about is we want the cosine. And we want the cosine multiplied by the power level of the light and the albedo of the surface. Okay, so there's some strange numbers here, but really this is the albedo, right? And so it's almost much like we were already seeing. The surface albedo tints the light, or the light tints the surface albedo, but really it's the reflected quantity, right? So in this case, we're 0 to 1. It's actually like probability math here. That what we're saying is, the reflective is, say, if it's 50%, then our albedo value is 0.5 on that channel. So it's like if it reflects 50% of the red light and scatters or absorbs the other 50%, then our albedo value is 0.5, and that's again the law of large numbers and so on. And here, unfortunately, light really has an intensity that's potentially infinite. Our lights can only go from 0 to 1. Either we say we're taking the full intensity of light or not. We'll talk about high dynamic range at some point, probably not in this talk, but at some point we might get there. But for when we're not in high dynamic range, we just kind of have whatever the value of your monitor is. So you either get the full brightness of your monitor at 1, or you get absolutely nothing at 0, and that tells you what color the light is that is actually incident on the surface. So why do we see here cosine theta and here we see n dot L? Let's dig into that a little bit. So the dot product is a way of scaling two vectors by each other. It's really a projection of one vector onto the other. It turns out, for any number of reasons that I don't necessarily want to get into, the dot product is equivalent to the lengths of the two vectors multiplied by the cosine of the angle between them. Now what's really happening is we're taking, we've got a vector like this that's x1, xy, right? And recall that a vector always starts at the origin, and really we're looking at, say, a 1, 1 value right here, right? So x1 equals 1, y1 equals 1. Here, x2 equals 0, and y2 equals 1. And we're multiplying and saying, okay, our final result is x1 by 2, so we get 1 in the x value. And then, we get a 0 because it's x1 times 0, so we'll get a 0 value. And then all we get is the value of y times y1 times y2, which is 1 in this case, because this is 1, 1, this is 0, 1, and so we get just 1 here. Okay, so you can also think of this as a projection of one vector onto the other. It really kind of works out regardless of which order you do the dot product in. If both of your vectors are unit length, and in this case, because we're talking about our light direction vector and our normal vector, they are unit length. We just know that they are. And unit length means that this is the length of a vector, this little symbol here. So we know that the length is 1 for vector 1, and we know the length is 1 for vector 2. Kind of the important piece here is that we can use dot product as a way of getting the cosine of the angle between them. Okay? Again, it's the cosine of the angle between them. Again, it goes back to the projection. I don't want to dig into the math on that. We'll just trust that's the case, but it's a very useful thing to remember because dot product is very cheap and cosine is very expensive. And so even in a graphics card, dot product is very cheap, and so we're going to use the dot product. And so that is why we have n dot L here, because what we're doing is saying we're going to take the dot product of the n vector with the L vector. So our light vector and our normal vector. And if they're matching, we're going to get the cosine of the angle between them, which if the cosine of the angle between them is 0, we get 1, or 100% intensity. And if the cosine of the angle between them is 90, then we'll get 0, because that's the way that cosine falls off. So here's a cosine here, right? So we get 1 at 0, at negative 90 or positive 90, we just get the thing, right? And it doesn't matter which side we do the angle on, right? So it's always, it's uniform, it's all uniform. Lambertian is very uniform. All right. So we looked at all that. Let's actually take a look at how we turn this into a Lambertian model. So the easy way to do that is to change our light parameter here. So this is all the setup for the light parameters, full forward shadows and so on. This surf function here, the fact that we said our surface is surf, means that we're going to go find the surf function down here. And so the standard model says we're going to do the standard lighting model, which has all of the things like metallic and smoothness. If we just say Lambert, now we no longer have light and smoothness. In fact, we'll just go ahead and get rid of metallic and smoothness, not light and smoothness. Yeah, so because we're doing a Lambert, we no longer have the surface output standard, we just have a surface output, right? And so we're just going to output our albedo. If this all still works, yeah, we're good. Okay, mostly. I guess we still have our parameters. Let me actually comment those parameters out just so we feel like we're really changing things. What you'll notice is that it didn't actually change that much, right? So it turns out that, you know, basically a smoothness of 0 and a metallic of 0 kind of implies that we want the Lambert model. So again, the Lambert is, you know, kind of the simple one, but as I said, it's the model that we're going after is that it's a very sort of rough surface, and so we assume that there's a rough character to our surface, and the light is going to bounce almost uniformly regardless. So small differences in the position make it bounce entirely different locations, right? Sort of chaos theory stuff. And what we say is, you know, that all of that bouncing, all of that difference comes down to the angle of the light, and we get a uniform distribution. So because it's a very rough surface, then we've got a Lambert model. It's also a very simple surface. So so metallic means that it's not very hard. It's a sort of a soft surface, and then our roughness is very, very high, or our smoothness is very, very low, I guess I should say. Okay, for this next example, I've gone in and actually taken I'm taking examples from here. This is the Unity surface shader lighting examples, right? This is a great place to kind of understand some of the ways this breaks down, but I'm just going to talk you through it. Okay, so we just looked at Lambert as it's provided by Unity, and it's really the normal Lambert, so it has a lot of the other lighting characteristics to it, like the fact that it can take the ambient light and some of those other factors. But let's actually look at that math, right? So let's put this side by side here and look at it. So again, we saw that it was the color of the surface times the color of the light, right? Filtered, you know, the reflected probability in this case, and then n dot L. And so we'll actually see that, right? So here we take the surface normal. Okay, so this is surface output, and it gives us the normal in this case. This is a function, so we've defined this, our lighting now is simple Lambert, and we're creating this lighting simple Lambert function. So our surface output actually comes from over here, right? So we're not getting the normal value, but it's provided for us. We don't necessarily have to copy the things in. The normal value comes in from here and comes out from here. We can specify, we'll actually do that, and we'll specify the normal value by creating a bump texture, but we'll do that in a minute. So we get our normal value coming from our surface output, so it comes from here. This is now again, we're seeing, okay, we created the surface function that sort of specified a lot of these things at the pixel value. Now we're actually going to do the light compute. And I know some of you might be thinking, I thought this was a sort of a shader thing, not a lighting thing. You were going to talk about lighting. There's other things to talk about lighting. Lighting and materials have a lot to do with each other, because really, you know, you don't get a color on a material unless you're lighting it. And the material specifies the shader property in a lot of ways is really what does this material do with the light that's impacting it, right? The material answers the question, what is this function here? What is this reflection function? You know, given a normal, given some incident light and a view angle, what kind of color am I actually going to show? Okay, so you know, in the very default case, all we show is our texture, but of course, you know, given the light, given our view angle, and many other potential things that we want to do here, we're going to change what that color is that we're putting out. Okay? So that's the way to think of this is, you know, the material color, you know, once we're getting down to the shader, we're thinking about what is the material substance that we're trying to deal with and what color is the output that we're going to do. Okay, so again, go all the way back and look at our Lambertian model, and the Lambertian model says color of the surface times the color of the light times the dot product, because we want to get this cosine law. And so we see that literally here. So here's the color, the albedo of the surface. Remember, albedo is the probability of reflecting a given photon at a given frequency, so a given channel. We take our light color along those same channels, we multiply the probability, and we really just get the law of large numbers. For those of you who are familiar with that stuff. And if you're not, don't worry about it. It's just multiplying the two together, and if it's 1, then it's the same. If it's less than 1, then it's like darkening it. And then we also either get the full value or 0 depending on the angle, right? So if it's, again, a 90-degree angle, if the light is really just glancing off the surface, then we're not going to get any color at all. And it's going to be, this value is going to be 0, this n dot L. Or if it's directly down, we get the full intensity of the light source. Okay. And what we get up here, this is really calculating it. We get this cool dot product function. So dot is like this function that we can use in this shader, which is awesome. We just get to borrow it. We don't really care about the fact. So Unity uses half here. It happens to be just a optimization. We could say float instead, but what we care about is it's all floating point numbers with some level of precision. This is a 4 value because it's color, right? So we need 4 values to represent color, including the alpha value. And then now, this color that gets output here really goes into the rest of the render pipeline and just gets put onto our screen, okay? The only other potential thing that might be modified is whether or not that light is getting shadowed, okay? So we actually get a light dir from every single light, or depending on our lighting model, we get some number of the lights passed into this one. And given those, then they will be shadowed or not shadowed. And that's kind of the only last little piece, is, you know, in terms of whether or not the color is going to show up on the screen. So let's look. We do see one big difference here. So let's come back and change this and look at that difference real quick. So if we do the Lambert model, we get the full light, right? And it's a little bit darker on this side, but what we're getting is the ambient light that's coming off of the skybox and all this stuff set from the lighting, and we'll talk about lighting in different set of lectures, probably. But here, with the simple Lambert, all we're getting is a very simple version, which is what is the light direction? And the light direction is specified by this light here, right? We only have one directional light in our scene. It's got one uniform direction, so we don't care about, you know, we don't get differences in the light direction within single pixels unless we're using like a spotlight. We'll actually change this light in a minute to look at that and see how that modifies things. So I'm going to bring this down a little bit so we can see it a little better. The only thing, you know, this is kind of the super simple version, right? So the only thing we care about is normal. The normal of the cube is uniform along the surface, right? So what we're seeing is, if we come over here, this normal is this way, this normal is this way, this normal is out this direction. In fact, yeah, so the normal here is following the red line. There's another normal going out that way. But the reason this is dark is because the light is not hitting that surface at all, right? So we're well past the 90-degree mark. Okay? So let me bring this angle down so that we're looking almost straight down at the surface. In fact, let me just set all of these. Oh, well, that one's not hitting the surface at all. All right, so now with this version, we're getting a little bit of light falling in on these guys for some reason. Maybe it's because, I don't know, there's probably some kind of error in some of this calculation. Yeah, so by going straight down like this, and I'm not sure why I'm getting a little bit of value here, maybe there's an error in my dot product or something. I'm getting the full intensity on this surface because the normal is matching the light direction, okay, at each point. If I go this way, now the normal is matching this light direction. Oh, I am getting some of the sky color even here. Did I actually save that out? Double check. I did save that out. Okay. Yeah, I'm still getting some ambient light, I think, in here, but that's all right. Well, and the sun color is changing, I think, too. Yeah, so now we're fully this direction. Let's rotate again. Let's make it go this way. And now we're fully mapped to this side, or more or less fully mapped. So now our cosine angle is fully there, right? But you notice that the surfaces, like the uniformity over the surface, is all like the same lighting level, right? So let's change that. In fact, I'm going to get rid of this. I'm going to make my sun not assigned to that. That way I can actually play with this. No, it's still doing that. All right, it doesn't matter. I'm going to disable my skylight here. I'm going to put a whole new light in. Yeah, we are getting some ambient light in there. That's okay. So I lied. There's a little bit of extra light. We drop a point light in. Now we can see a little bit of difference in our surface. Okay. So what's happening here is the point light is really a single light source where the rays come out like this, right? And hopefully you can see my mouse okay and see kind of what's happening. And so the rays here are full intensity, right? Because the rays close to where the light source is are going straight towards the surface, right? So we're drawing straight from here into here, straight from here into here, very close to straight from here. But what you then start to see is the fall off from the angle because the light's coming in at a steeper angle, right? It's no longer straight in, it's no longer perfectly matching the normal. And so we're still seeing the Lambert model in general that, you know, no matter where we're looking at, whatever view angle we have, we always see the same light intensity. We don't care about our view angle in this case. But we do see a difference depending on the angle of the light because now the light is no longer sort of a uniform direction like it is sort of when we're assuming the sun. Right? The sun's so far away that we just assume that it's always kind of uniform direction, right? Yeah, so if we get really close, I think I'm just getting inside the model. Yeah, if we get really close there, now we see that you know these angles that it falls off very quickly. Okay. All right. So yeah, just to review, let's come back here. So all of this is, again, we're looking up our texture here by doing the text 2D, multiplying by a color if we want to. In this case, we're just multiplying by white. And then we're outputting to a lighting parameter to say, okay, given that albedo color, how am I going to modify my light source? So now let's assume that we're no longer, you know, we're going to assume, so we've got two levels of roughness, right, or two levels of normals in some sense. We've got the normal of our cube itself, which is flat along here, so it's exactly the same normal along this entire face. But let's put a bump map in there, okay? And we'll use that bump map to then give us a smaller amount of normal map, okay? I'm sorry, a smaller amount of roughness. And then the final sort of level of roughness, so there's three levels of roughness that we can think of. We've sort of got the overall shape that we model into our polygons themselves, right? So, you know, we could put many more polygons and make a bunch of different, you know, changes in the surface rather than having it be a single flat one. We could do a texture bump map to say that it's got some smaller normals. And then finally, because we're using a Lambert model of lighting, we're saying it's a very rough surface in that sense because we're assuming almost quantum mechanical levels of roughness where the light's going to bounce off different, like the photons are bouncing off differently because of the changes in the microsurface. Yeah, that'll come back to, you know, if we're a really strong metal surface or a really strong smooth surface, then we're going to get a different kind of result. That we're going to get a reflective result, as we were seeing earlier, and that's actually talking about the microsurface that's there. Okay, so let's create, I'm going to use this grayscale map and just create a normal map in Unity this way. There are other processes to create normal maps. That is really a topic for another class, usually a modeling class. Drop the bumpiness quite a bit here because it's a little bit too bumpy. That's a little better. This is a method that is used in some of the, in fact, this is a method that you use to do from bump map to normal map, right? So the normal map actually specifies in the colors here our direction. So let's take a minute to look at that. So this is a normal map. Hopefully you kind of recognize that purpley color. If you're doing bump maps, you get a grayscale, and then you just turn them into a normal map in this kind of way. And usually the tools like Maya and whatever other tool you might use will also have this kind of stuff in there. The idea behind a normal map is that we are using the fact that we have an RGB vector and those floating point values. We're using that to actually represent our vector, right? So really, R is our X value, B is our Y value, and then G is our Z value. So the reason it's purple is that, let's see, Z is coming out, so Y is going up to the top, or if we start at the bottom to the top, that's the direction that Y goes. X, as usual, goes from center to right, unless you're in Unreal, and then for whatever reason it goes forward. I don't understand why. And then Z comes out. Okay, so Z being green. Is that true? Maybe I'm a little off here. It might be that Y is coming out and Z is going north. I think that might be the case in this sense. So we see Z values actually coming off the top here. So we get a strong green value because the vector, the normal, at this point is going this direction. Now notice that, again, this is not really a real surface, right? This is color that is representing small changes in the normal value. So you're not going to see these bumps necessarily, especially if you look from the side, right? So if your eyeball is coming from the side, you're not going to notice bumps like this. But if you're kind of looking at an angle, then these shadows add a little extra information to your eye to give you a sense that you're seeing this, right? So that's the whole trickery of this. And so by looking up or using a normal map in this way, we are sort of tricking our eye by using the response of the light to give us either light or shadow, depending on the response. So let's take a look at how we actually put that into the shader itself. Okay, so the first thing we're going to have to do is actually bring in a normal map here. I think kind of what we need here, rather than white, we're going to say bump in order to specify that this is a normal map or a bump map. Sometimes they're used interchangeably. I think bump maps are often grayscale values to represent the bumpiness, like black is low and white is high in that case, and then normal maps are, of course, the encoding that we've got there. Okay, so then we're going to look up our, I'm just going to use a float for this text 2D. If I called it normal map, we're going to see that this is not quite right. So a couple things I need to add. I have to add a sampler 2D, which says that we're going to allow a sampling on this, the kind of UV sampling that we do, and we're also going to have to pass in our normal map value. Now thankfully, again, Unity is going to know to just bring in this UV linear interpolated across the whole thing, right? So we're going to get a whole new set of UV values coming from this, and it's going to give us well, it's like a map as well. So we go back and look at Unity. We look at our cube here, or actually let's just look at the test material. We now have this new normal map. We get a new set of tilings and offsets to modify those if we want to. We get our normal map. We're currently not doing anything with that normal value, of course, and we're actually not capturing it correctly. So to capture it correctly, what we need to do is this unpack normal. And what this says is there's actually some minor differences in the fact that the way this is represented doesn't quite match up, and we have to actually take the color that's here and multiply it by 2 minus 1. That way we get both positive and negative values. Things like that are what's happening here. Otherwise we'd only get 0 to 1 values, and we wouldn't really be able to represent it down correctly. So let's not worry about that. Let's just know that we need to unpack our normal. And then in this case, we're just going to pass our normal straight out, right? So we said float 4, and it's really a float 3. Okay, so if that's all good, then we should not have any errors. And it appears we don't have any errors, which is good. If we did have errors, in fact, let's take a look at that. So let's just have some random one here. One, we will see weird things happen, right, to our shader. And then we'll get like a little error over here. So this is a little bit like our normal Unity compile issue. Sometimes it goes away over here. So if I hit the clear button for some reason, I lost my shader because it didn't try to recompile it. But you can always go look at your shader and see what is the error I'm getting, right? And double check that I'm recording. That's good. That'd be terrible if I wasn't. All right. So coming back over to Unity, if we see color, if it looks like it's working, then yay, we're kind of seeing the thing. Make my icon there a little bit smaller. All right, so let's drop our normal onto, drop our normal onto the material, because that's where we want it really. And now we actually see color differences, right? So maybe the only case that we want to kind of take a look at is over here. And this is where, the direction of the light really matters and comes into play. So we're getting more angles, and so we'll actually get brighter colors down here because some of these angles of the micro normals, or the bump map normal, is pointing towards the light, right? So some of these, they're pointing towards the light, some of them are pointing away from the light. And we're getting the sense of depth because we're capturing that, but we don't actually have any depth, right? This is a perfectly smooth surface because it's 2 triangles total. I mean, if we look at it from the wireframe, we see there's exactly 2 triangles if we do the shaded wireframe. Again, we still see there's no extra information in the triangle shape, in the overall normal, but if we combine that with the normal map normal, and now we're getting that, right? Now we might actually want, so this is a flat surface, and that's great. We are only sending in this normal. We are actually ignoring the input normal, right? And so we could, if we wanted to, I'm not going to try to do it here. What we'd actually do is supplement both the normals together, right? So if we had a surface, or like a sphere with a smooth normal that was going over the surface, right, from our vertex to vertex, we could use that as a sort of base normal, and this is then a modification to it. And really what we do, in fact, I think I can just do in normal, see if that compiles, and I want to normalize this. So normalize is another one of those cool functions that makes sure our normal is of unit length, right? Because again, we're depending on the fact that our normal is going to be unit length to get that cosine thing to work up here. Come back over here, and no, I did something wrong. Oh, I think I need to actually say I want my normal to go through. Do that, does it work? It does, okay. So it didn't really change anything over here because we're not doing normals, but let's put in a sphere and add in our object, and then we can double check the difference between those two. So let's put a sphere up here. I want to, we see our light coming down. Let's give it the material as well. And yeah, so it would be hard to notice because we get so many of these triangles anyway. But if we don't include this, let's see if we can look at this side by side to see how this changes as we do this. Let's see, so I'll just comment this out, and then as I save it, come back over to Unity, we might see a minor difference between the two. It's going to be hard to tell. Yeah, you can kind of see it. So, so here we're getting the full normal, or we're kind of just relying on the normal of the texture itself, and then here we're actually using the normal that's coming from the sphere itself and adding that in. Come back, and it's a little more correct, I'd say. Yeah. So we do. I think that's actually pretty noticeable. So yeah. So again, with a cube like this, we don't care so much, but with the sphere, it becomes much more interesting because, of course, we want the sphere to have that spherical quality that spheres have, right? All right. So so we've kind of fully covered the Lambert model at this point. What if we did want more reflection, right? So the Phong model is really another simplification, but now what we're assuming is that the microsurface is very smooth, right? So rather than in the Lambert model where we're assuming that it's kind of rough and that somewhat randomly, depending on some quantum mechanical properties, the photons are going to get reflected in slightly different ways depending on the tiny roughness bits that are at that point, right? That tiny little point we're hitting. Here, what we're saying is it's perfectly smooth, and that every single photon is going to be aligned perfectly. And that really means that we're going to see a reflection, a proper reflection, right? And so what we then expect to find is, rather than needing to only care about the light and the normal, right? Because that's, again, all we care about is the light and the normal up here, because we're just going to kind of assume a uniform distribution of the light scattering off of there. Now we need to know where the eye is coming from. Okay, we don't need to know where the eye is looking, because we're just going to send light in the direction of the eye, and if you're looking in the right direction, good. If you're not, then that's fine. You're just not going to see it. So we don't care where the eye is looking, right? So I could be looking this way, I could be looking that way. We just care that my eye is over here, right? So what that means is we care about the position of the camera. We don't actually care about the direction the camera is looking, okay? Which is useful. Okay, so the thing that we're going to need to know now is the reflection vector. And the reflection vector is the vector that forms sort of a 90-degree angle around the normal, right? So if we look at, or I guess it's exactly the same, it's not a 90 degree, it's the reflected angle off of here. All right, we're going to keep that, or I'm going to trim it. Okay, so given that our light has this angle, then our reflection vector has exactly the same angle over here. And what we need to know then is whether or not our view direction matches the reflected vector. Okay? And then using that, we have what's known as a specular response curve that we can use. Okay? So if we have a really smooth surface, we're going to have a strong exponential curve like this one, and it's going to fall off very quickly. Right? Again, we still essentially have the cosine effect. So if we're perfectly aligned, then we get a full. Actually, this fall off is exponential, but we still use the cosine of the angle between them. But we get now we care about how close we are to the reflection. So if it's a very sort of hard surface, very high metallic quality, then we're going to get a very tight specular response. And if it's a very plasticky surface, we're going to get a lower specular response. But in either case, we're kind of assuming a strong smoothness, right? So the Phong model really assumes it's very smooth and that we care a lot about the reflection because all of our energy, almost all of our energy, is along this reflection vector. And then depending on the hardness of the surface and how much might be scattered versus absorbed, like so if it's hard surface, then everything gets scattered. If it's a very soft surface, then, if it's a hard surface, everything is reflected. If it's a soft surface, more gets either absorbed or scattered, right, by being partially absorbed and then re-reflected out in a different way. Okay, so looking at this specular, we've created a new lighting function, specular lighting here, where actually what we're doing is, rather than computing the reflection vector over here, we're really going to compute the half vector between the normal and the view, right? So the half vector is exactly split between these two. This trick creates that half vector. You just normalize with the two of them added together. I don't know how to specify that entirely, but generally we're always going to be within 90 degrees of each other. We will get a zero vector if they're sort of evenly dispersed on opposite sides of the position of the surface that we're looking at. But it kind of doesn't matter. So for the most part, this trick gives us a halfway point between these two, and then we compare that with the normal, and that's how we get our reflection, right? So it's kind of a tricky version of doing exactly the same thing, finding the reflection without having to actually figure out computing the reflection vector, which is a possibility, but we're not going to worry about that. So we take our normal, we dot it with the h vector in this case, and then we take that h, that dot product, and we do an exponential, and so that comes to this exponential fall off here. So we've got a very high exponential. We've got an exponent of 48, which has a very steep fall off, which means it's very highly reflective. I'm going to drop that. Well, I'll leave it here for now. We'll look at what that looks like. And I had to change the function up here, and then change the fall off here. I did leave off attenuation up here. Attenuation, this value. Oh, and we'll notice we've actually got the view direction added in. We could have potentially had it up here. We just didn't need to because we didn't care about the view direction Lambert. Attenuation is the further away you get from the light, the less power it has, because it just sort of gets absorbed in space. Unless you don't assume that, like it's a star with full power and it's traveling through a vacuum, and then you don't have any attenuation. But attenuation is kind of capturing like traveling through the atmosphere in a simple version of doing that as well, and usually the right thing. Okay, so we see our specular lighting here, right? So most of our light is coming from exactly where the light source is, right? All right, so yeah, so we're getting our reflection vector here, or sorry, our specular reflection with a high exponent. We can actually very strongly see our normal map, right, where the light is hitting it and all that kind of fun stuff. And yet now we notice that as I move my position in space, that where the strongest parts of the reflection are changes, right? Which is what we'd expect. Yeah. And but it doesn't care about the angle of my eye, right? It doesn't care whether I'm looking at it. It only cares about my position in space and whether or not I'm going to get hit with a light from that or not. Okay, so so you'll see some extra code in here. There's a diffuse piece, and it's actually just bringing back in our Lambert. So the Lambert is the standard diffuse. We could actually come in here and say, let's just add them together, right? So it's really a combination of the two to say, well, I've got the specular component, and I'm also going to do the diffuse component, and what we get is something a little bit of a combination of the two. We might actually say, well, let's do half of each, right? Because really, we don't want the number, the component to be that much higher, and so now we get a little bit of both. We can get a little bit of diffuse, a little bit of light. Really, what we're saying when we're doing this is actually picking our smoothness value, right? So in a sense, what we're getting is a 0.5 smoothness in this case, or we can say I want 100% reflection in this case. And of course, we're not really getting all of the reflections. We're not capturing like the skybox reflection, things like that, the metal surface is showing us. But this starts to give us most of what we're getting out of the normal shader, right? So if we go all the way back and we say, no, I'm actually going to go back to the standard lighting model, and I'm going to do standard output, then what we'll see is, oops, I need to give us metalness here, right? So with a smoothness of nothing, we get exactly that, and with a high smoothness and high reflection, it starts to look very similar to what we had before, right? Now we're losing a few things. We're getting higher exponent. Let me come back and show you that exponent. In fact, the smoothness really has more, kind of aligns more with the exponent in some ways than, and this is maybe more like if I'm going to do the diffuse model. Now it's also putting in reflections of the skybox as well, and so there's a lot more going on here. than what we're adding in. But if I put the smoothness down to something like that, then we start to see, it looks a little bit like what we had before, right? So let me put that back. Get rid of these guys again because they don't exist within the shader model, or in the simple shading model. So I could probably just save that input output and reuse it here. Yeah, so it's very similar, right, to that. And then if we wanted to start to model, say, that really high-end specular value, that's by increasing this exponent very large, or we can put the exponent very small. We start to see, like, well, that's like the smoothness is way low, right? So really the smoothness in the normal shader is a lot to do with the exponent, the fall off, right? So again, the fall off of how quickly we're moving away from the reflection vector, right? The further away from the reflection vector we are, the faster we're no longer getting a strong reflected light component. Okay? I would normally at a point like this start to say, does that make sense? But you can't respond to me. However, have the option to come to class on Friday to meet me in Zoom and talk about these things.